Never touched anything. You put your hand flat on a table and press down. It feels solid. It feels like contact, the most obvious fact in the room. Your palm is on the wood is under your palm, and there is nothing at all in between. There is something in between. The electrons in the outer shells of your skin and the electrons in the outer shells of the table never actually meet. They repel each other through the electromagnetic force, and that repulsion climbs steeply as the distance shrinks. What you experience as touch is that repulsion traveling back up through your nerves. The gap is roughly 100 millionth of a centimeter wide, which is small enough to be invisible and large enough to be permanent. Solidity, then, is a sensation rather than a fact. Atoms are almost entirely empty space. Scale one up to the size of a football stadium, and the nucleus is a grain of rice on the center spot, with the electrons a faint blur somewhere near the back row. You are mostly nothing. The table is mostly nothing. The firmness you feel is two clouds of nothing refusing to occupy the same place, and that refusal is strong enough to hold up a building. So every handshake, every hug, every time you have rested your forehead against a cold window on a long drive, a sliver of space stayed open. It is not a lonely fact. It is the reason anything has an edge. The same stubbornness that keeps your hand out of the table keeps the table out of your hand and out of the floor, and keeps you from sinking quietly through the world. Pauli Exclusion. Stand still for a moment and consider that you are not falling. The floor holds. The chair holds. Somewhere beneath you, the ground holds. And beneath that, rock holds up rock all the way down for thousands of miles without giving way. Electromagnetic repulsion is only half the reason. The other half is a rule discovered by Wolfgang Pauli, and it is stranger than a force. No two electrons can ever occupy the same quantum state at the same time. Not because something pushes them apart, but because the mathematics of reality simply does not contain a version of the universe in which they overlap. It is a prohibition, not a pressure. That prohibition is why matter takes up room. Squeeze a lump of anything hard enough, and the electrons get crowded into fewer and fewer available states. Since they cannot double up, they are forced into higher energy levels, and pushing them there costs more and more energy. This resistance is called degeneracy pressure, and it does not care about temperature. Cool the material to almost nothing, and it still refuses to compress. It is the only kind of pressure that survives at absolute cold, and it is the reason a lump of iron has a size at all. Whole stars rest on this. When a sun like ours dies, gravity crushes the leftover core down toward the size of the Earth and then stops, because the electrons will not share. That is a white dwarf, held up by a rule about bookkeeping. Push past a certain mass, and even that fails. The electrons merge into the protons, and the object collapses into a neutron star held up by the same rule applied to neutrons instead. Everything with a surface, everything you have ever stood on, is standing on a technicality about counting. 0-point energy. Cool something down. Keep going. Take the heat out slowly until the molecules are barely shivering. Then take out more until you are within a whisper of the coldest temperature the universe allows. Common sense says that at the very bottom, everything stops. Nothing stops. There is a residual motion left over that cannot be removed by any amount of cooling, and it is called 0-point energy. It falls straight out of the uncertainty principle. A particle sitting perfectly still at a perfectly known location would have both a definite position and a definite momentum at the same time, and that combination is not something reality offers. So the particle jitters forever. The jitter is the price of not being contradictory. You can watch this rule bully an entire element. Helium, cooled all the way to the bottom under ordinary pressure, refuses to freeze. Every other substance surrenders and becomes a solid. But helium atoms are so light and so weakly bound that their leftover motion is enough to keep shaking the crystal apart as fast as it forms. To make solid helium, you have to squeeze it under about 25 atmospheres of pressure and physically hold it in place. Left alone at ordinary pressure, helium stays liquid all the way down, the one substance in the catalogue that never surrenders to the cold. There is something worth sitting with here. Stillness, absolute and total stillness, is not a state the universe has ever contained. Not in the deepest vacuum between galaxies, not in the coldest laboratory ever built, not inside the atoms in your own hands. At the very bottom of everything, there is a tremor that has been running since the beginning and has no mechanism for stopping. Quantum tunneling. A wall is a promise. It says you are on this side and whatever is on the other side stays there. Bank vaults are built on that promise. So are prison cells and skulls and the thin insulating layers inside every chip in your phone. The promise is statistical. A particle approaching a barrier it does not have the energy to cross does not simply bounce. Its wave function leaks through to the far side and thins out as it goes, which means there is a small but genuinely non-zero chance the particle appears over there instead. It did not smash through, and it never had the energy to climb over. It was just, with some probability, already on the other side. This is quantum tunneling, and it is measured constantly. Scanning tunneling microscopes work by counting the electrons that make the jump, which is how we get pictures of individual atoms. The sun runs on it. 2 protons in the core need to get close enough to fuse, but their mutual repulsion is far stronger than the temperature can overcome. By classical rules, the sun should not be burning. It burns because a tiny fraction of collisions tunnel through the barrier anyway, and there are so many protons that a tiny fraction is enough to light a star for 10 billion years. The same effect is currently ending the age of shrinking computer chips. Insulating layers are now a few atoms thick, and electrons tunnel across them and leak. You cannot engineer this away because it is not a flaw in the material. So the next time something feels safely sealed off, remember that the seal is a probability, and probabilities do not promise. They only make things very unlikely for a very long time. Vacuum isn't empty. Pump every atom out of a box, then cool it toward the bottom of the temperature scale, shield it from every field you can think of, and hold it in the deepest silence that engineering allows. What you have made is a vacuum, and it is still full. Quantum field theory does not permit true emptiness. Fields fill all of space, and by the same uncertainty rule that forbids stillness, those fields cannot sit at exactly zero. They fluctuate. Pairs of particles flicker into existence and annihilate again on timescales too short to catch directly. Physicists call them virtual particles, which is a slightly misleading name for something with entirely real consequences. The fluctuations are not a bookkeeping trick either. They shift the energy levels of hydrogen by a measurable amount, an effect called the Lamb shift, which was pinned down experimentally in 1947. The consequences are measurable in a laboratory. Put 2 uncharged metal plates extremely close together in a vacuum, and they will be pushed toward each other. The gap between them excludes certain fluctuation wavelengths, so there is slightly more activity outside the plates than in, and the imbalance produces a force. That is the Casimir effect, and it has been confirmed repeatedly. The vacuum pushes. There is a bigger version of this problem that nobody has solved. When theorists add up the energy the vacuum ought to contain and compare it to the energy actually driving the expansion of the universe, the two numbers disagree by a factor with more than 100 zeros after it. It is the worst prediction in the history of physics, and it is sitting right there, unresolved, in the emptiest thing anyone can build. Even nothing has an unpaid bill. You live past. You are reaching for a glass of water on the desk in front of you. It looks like it is happening now. The glass is there now. Your hand is moving now. The whole scene has the obvious quality of the present tense. None of it is now. Light took time to reach your retina. The retina took time to convert it into signals. And those signals took time to crawl through several stages of visual processing before anything reached awareness. Add it up, and the world you are consciously seeing is somewhere between 80 and 200 milliseconds old, depending on the conditions and who is measuring. Touch is slower still from your feet than from your face, because the nerve has further to travel. Your brain hides the lag by predicting. It runs a forward model, guesses where the moving thing will be by the time the signal lands, and shows you the guess. This is why a well-hit cricket ball can be intercepted at all, given that a batsman has less reaction time than the ball needs to arrive. It is also why certain optical illusions work. Push the prediction into a situation it did not evolve for, and you can watch it break in a controlled way. The flash lag illusion is the standard demonstration, and it fools everyone who sees it, every single time. What this means is that awareness is a broadcast, not a window. There is a small studio somewhere behind your eyes, assembling a version of the present from slightly stale material, and it has never once been caught doing it. You will not feel the delay while reading this sentence. That is the whole trick. The edit is finished before the footage reaches you. Brain deletes time. Look at yourself in a mirror. Look at your left eye, then your right eye, then back again. Do it a few times. You will never once see your own eyes move. Ask somebody else to do it, standing next to you, and their eyes move, obviously, dramatically, impossible to miss. The reason is a process called saccadic masking. When your eyes make one of those fast flicking movements, called a saccade, the visual system suppresses the incoming blur so that you are not treated to a smear several times per second. It does not just hide the blur. It stitches the moment shut, backdating the image you see afterwards so the timeline appears continuous. The suppression begins before the eye has even started to move, which means the system commits to the edit in advance. You can catch the seam. Glance suddenly at an analog clock with a ticking second hand, and the first second often appears to last too long. That stretched second is the gap being filled in with whatever the clock looked like when your eyes landed. Researchers call it chronostasis, and the arithmetic is uncomfortable once you total it up. Between 40 minutes and a full hour of your waking day is edited out this way. You blink for a related reason and lose more time again, and you have never once noticed the room going dark. The genuinely strange part is not the blindness. It is that the same system that deletes the footage also deletes the record of the deletion. You have no sense of missing time, because the thing that would notice is the thing doing the cutting. Your continuous, seamless experience of a Tuesday afternoon has holes in it, and the holes are invisible by design. Blind spot. Somewhere in your field of view right now, off to the side of center in each eye, there is a patch where you are completely blind, not blurry, not dim. There are no photoreceptors there at all, because that is where the optic nerve punches through the back of the retina to leave the eye. The classic demonstration takes 10 seconds. Draw a dot and a cross on paper a few inches apart, close your left eye, stare at the cross with your right, and move the paper slowly towards you. At some distance, the dot simply disappears. Keep moving and it returns. It never goes grey or fuzzy. It vanishes into whatever colour the page happens to be. That last detail is the important one. Your brain does not leave a black spot, because a black spot would be information. Instead, it fills the region with a plausible continuation of the surroundings, extending the pattern, the colour, the texture of whatever is nearby. If the blind spot falls on striped wallpaper, you see stripes. The stripes are invented. They have the same felt quality as the real ones. People who lose patches of retina to disease often report no gap at all, because the filling in continues straight over the damage and hides it from them. Which raises the question of how much else is being filled in. The answer, from decades of vision research, is a great deal. Detailed color vision covers only a small central region. Peripheral detail is largely reconstructed from expectation. You are not looking at the room. You are looking at a fast, confident model of the room, checked against reality only where it matters, and you have never had access to the raw feed. Diffraction limit. A microscope is a simple bargain. Put more glass in the way, grind it better, and you see finer detail. That bargain held for 3 centuries of steady improvement, and then it stopped, not because the lenses got worse, but because there is a flaw. Ernst Abbe worked it out in the 1870s. Light is a wave, and a wave cannot resolve features much smaller than about half its own wavelength. Visible light runs from roughly 400 to 700 nanometers, so no arrangement of lenses, however perfect, will ever separate 2 points about 200 nanometers apart. They blur into one. This is the diffraction limit, and it is not an engineering problem. It is a property of waves. Everything that images has to live with it. Radio telescopes need dishes kilometers across because radio waves are meters long. Chip manufacturers move to shorter and shorter wavelengths for exactly this reason, ending up at extreme ultraviolet light produced by hitting droplets of molten tin with a laser, because that was easier than beating the limit. Electron microscopes see atoms because electrons have vastly shorter wavelengths, not because their lenses are better. The wavelength of a fast electron is thousands of times shorter than visible light, and the limit simply moves down with it. Clever people have found ways around it in specific cases, using fluorescent molecules that switch on and off so their centers can be located one at a time. That work won a Nobel Prize, and it is worth noticing what it actually did. It did not break the limit. It sidestepped the question by measuring something else and inferring the answer. The wall is still there. People just learn to go around. Heisenberg Uncertainty. You want to know 2 things about a particle: where it is and how fast it is going. These feel like separate questions, the way a car's location and speed are separate questions, and it feels obvious that with good enough equipment you could pin down both. Werner Heisenberg showed you cannot, and the reason is worse than clumsy instruments. It is often taught as a measurement problem, as though looking at something inevitably disturbs it. That version is not quite right. The deeper statement is that a particle does not possess a sharp position and a sharp momentum simultaneously. The 2 properties are linked the way the pitch and the timing of a note are linked. A sound with a perfectly defined frequency must last forever. A sound lasting an instant contains every frequency at once. Sharpen one and the other necessarily smears. Multiply the 2 uncertainties together, and the product can never fall below a specific small number set by Planck's constant. This is not a suggestion. Every attempt to beat it has failed, and the reason it fails is that there is nothing there to measure more precisely. The same relationship binds energy and time, which is why unstable particles have a fuzzy mass, and why the shorter a particle's life, the less definite its energy is permitted to be. The consequences leak upward into things you can see. It is why atoms have a size instead of collapsing, why the sun's core behaves as it does, why absolute stillness is unavailable. And there is a quiet philosophical bruise in it that people still argue about a century later. The universe does not merely hide certain facts from you. In some cases, it declines to have them. Universe isn't local. Two particles are created together and then carried apart. Measure one and you instantly know something about the other, however far away it has been taken. For decades, the sensible reading was that they simply left the factory with matching instructions. The way two gloves posted to opposite ends of the country were always a left and a right. John Bell killed that reading in 1964. He worked out that if the particles really did carry hidden instructions, and if nothing travelled between them faster than light, then the statistics of repeated measurements had to obey a specific ceiling. Quantum mechanics predicted results above that ceiling. So this was no longer philosophy. It was a number you could go and measure. Bell called his own result the most profound discovery in science. They measured it. Alain Aspect in the early 1980s, then better experiments, then better ones again, each closing a loophole the skeptics had pointed at. By 2015, the last serious gaps were shut. The ceiling is violated, comfortably and repeatedly, and the three physicists behind that work were given the Nobel Prize in 2022. Alain Aspect, John Clauser, and Anton Zeilinger shared it, and the citation named the experiments rather than any new theory, which tells you how badly the field wanted an answer it could hold. What follows is genuinely hard to swallow. At least one of two comfortable assumptions has to be abandoned. Either properties do not exist until measured, or distant things can influence each other in a way that ignores separation. Most physicists give up the first. Either way, the tidy picture where every object quietly carries its own complete set of properties around with it, waiting to be read, is gone. It was tested. It lost. Entanglement can't message. Faster than light messaging is the first thing almost everyone reaches for once they hear about entanglement. Two linked particles, one on Earth and one on a ship near another star, and a way to talk across the gap with no delay. It seems like it should be sitting right there, waiting to be engineered. It is forbidden, and the proof is called the no communication theorem. Here is the problem. When you measure your particle, you get a random outcome. You cannot choose it. The distant partner's outcome is correlated with yours, but its statistics, looked at on their own, are exactly what they would have been if you had done nothing at all. Your friend sees noise. There is no pattern in the noise that depends on your choices, because you had none. The correlation only becomes visible when the two sets of results are brought together and compared. That comparison requires sending the results by ordinary means, at or below the speed of causality. The strangeness is real, and it is completely useless for sending anything. Quantum teleportation does not dodge this. It moves a state from one place to another, and it still requires two ordinary bits to travel by radio or fiber before anything can be reconstructed at the far end. This is one of the tightest fences in physics, and it exists for a reason. If entanglement could carry a message, relativity would allow that message to arrive before it was sent in some frame of reference, and effects would precede causes. Instead, the universe permits a correlation stronger than any classical explanation, and then, with what looks almost like deliberate care, arranges for it to be unexploitable. You may look. You may not use it to talk. No cloning theorem. Photocopiers are unremarkable. Point a machine at something, read it, produce an identical version, keep the original. That pattern runs through everything from printing presses to cell division to the file you duplicated on your desktop this morning, and it is so ordinary that it feels like a basic capability of the world. Quantum states cannot be copied, not by any device, however advanced. This is the no-cloning theorem, proved in 1982, and it is startlingly short. Quantum mechanics is linear, and a machine that perfectly duplicates arbitrary unknown states turns out to violate that linearity. 2 lines of algebra and the whole possibility collapses. The reason it holds is tied to everything in the last few chapters. Reading a quantum state disturbs it, and you cannot read enough to reconstruct it without destroying the thing you were reading. There is no sneaking a look first. The information is not sitting in the object waiting to be transcribed. Measurement is not a passive act of reading. It forces a definite answer out of something that did not have one, and the original is gone. The practical consequences are large and mostly good. Quantum key distribution works precisely because an eavesdropper cannot copy the transmitted states and pass the originals along. Any attempt to intercept leaves damage that both parties can detect. On the other side, it is the central obstacle in building quantum computers, because ordinary error correction relies on making backup copies, and that route is closed. Engineers had to invent an entirely different kind of error correction that never looks directly at the data it is protecting. An entire field of error correction exists because of a proof that fits comfortably on the back of an envelope. Kolmogorov Complexity. Write down a string of 1,000 random letters. Now write down the letter A repeated 1,000 times. Both are 1,000 characters long, but the second one can be described in a handful of words, and the first one cannot be described by anything shorter than itself. That difference has a formal name. The Kolmogorov complexity of a string is the length of the shortest program that outputs it. Simple, pattern things have low complexity. Random things have complexity equal to their own length, because the shortest way to say them is to say them. It is a clean definition, and it leads immediately to an uncomfortable counting fact. There are far more long strings than short programs. If you want to compress every string of 1,000 bits into something shorter, you need a distinct shorter output for each one, and there simply are not enough shorter strings to go around. Most objects, the overwhelming majority, cannot be shortened at all. Compression works in practice only because the things humans care about, photographs and speech and text, are wildly unrepresentative of all possible data. Photographs of the real world occupy a microscopic corner of the space of all possible images. Almost every arrangement of pixels is static, and nobody wants to store static. There is a final twist that keeps mathematicians up at night. Kolmogorov complexity itself cannot be computed. There is no program that reliably tells you the shortest description of an arbitrary input. So the universe contains a well-defined measure of how simple a thing is, and denies you any general method of finding it. You can establish that a specific string is complex only in a limited set of cases, and past that, the question is formally out of reach. No universal compressor. Somebody, somewhere, is always announcing a compression breakthrough. Any file, any size, down to a fraction, no loss. The pitch decks are convincing, and the demonstrations often work on the sample data provided. Investors have been separated from real money by this claim more than once. It is impossible, and you do not need physics to see why. You only need to count. Suppose an algorithm takes every possible file of a given size and makes it smaller with no loss. That means every input maps to a distinct, shorter output, since otherwise you could not tell which original to restore. But there are fewer short files than long ones. Two different inputs must land on the same output, and at that moment, the process is no longer reversible. This is the pigeonhole principle, and it is about as arguable as 2 plus 2. Every real compressor obeys it. Formats like zip make common data smaller and, quietly, make unusual data slightly larger. Run a compressor on an already compressed file and watch it grow by a few bytes. Those bytes are the cost of the promise being kept honestly. Run it a second time and it grows again. There is no fixed point at which a file finally becomes pure information. What that means is that compression is not a technology for removing waste. It is a bet on what kind of data you will see. English text is redundant, photographs have smooth regions, audio has predictable structure, and every algorithm is an encoded guess about which patterns show up. There is no universal winner, only a set of trades, and someone always pays. Every format is a theory about the world, and the theory is the only reason it works. Shannon capacity limit. You are on a bad phone call. The other person keeps breaking up, you keep saying the last few words again, and eventually one of you switches to text. It feels like a hardware problem. Better signal, better microphone, better line, and it goes away. Claude Shannon proved in 1948 that every channel has a hard ceiling on how much information it can carry, set by its bandwidth and its noise. Below that ceiling, you can push the error rate as close to zero as you like with sufficiently clever coding. Above it, no coding scheme in existence or yet to be invented can get your message through reliably. Not a better one. Not any one. This is the reason your phone has bars and your broadband has a number attached to it. Engineers are not chasing perfection, they are chasing a known finish line. Modern error-correcting codes get within a fraction of a % of the Shannon limit, which is one of the quieter triumphs of the last century, and there is nowhere further to go. Turbo codes and low-density parity check codes reached that region in the 1990s, and modern phone standards use them because there was no further prize left to chase. The result reframes noise itself. Noise is not merely annoying, it is a tax with a published rate. Double the noise power and the ceiling drops in a way you can calculate before building anything. Deep space missions, undersea cables, and the storage in your pocket are all designed against this number. Shannon did not just describe communication. He drew the edge of the map and then showed that the edge is reachable and the far side is empty. Nyquist sampling theorem. Watch a car advert closely and the wheels sometimes turn backwards. Helicopter blades in films occasionally hang motionless in the air while the machine flies. Nothing is wrong with the camera. You are watching a mathematical law being violated on purpose, for style. The rule is the sampling theorem, usually credited to Harry Nyquist and Claude Shannon. To capture a signal without ambiguity, you must sample it at more than twice its highest frequency. Sample slower, and the fast components do not simply vanish. They fold back down and reappear disguised as slower ones, indistinguishable from the real thing. That is aliasing, and once it has happened, no processing can undo it, because the information needed to tell the two apart was never recorded. This is why compact discs sample at 44,100 times a second. Human hearing tops out around 20,000 cycles per second, so twice that plus a margin for filtering gives the familiar number. It is also why every digital recorder has an analog filter in front of the converter, removing frequencies too high to capture before they get the chance to masquerade as low ones. That filter is not optional, and it is part of why cheap converters sound worse than expensive ones, running at the same rate. The wider lesson applies far outside audio. Anytime you measure something periodically, whether it is a heartbeat, a stock price, or a satellite passing overhead, you are choosing a ceiling on what you can ever detect. Things that move faster than your sampling rate do not go unnoticed. They come back wearing someone else's face, and you will believe them. Astronomers collide with this constantly. A survey that photographs the sky once a night will misread a star that pulses faster than that. Chaos prediction horizon. The forecast says rain on Thursday. It is Monday. By Wednesday, the forecast says Thursday is dry, and on Thursday, it rains. The instinct is to blame the meteorologists, or the models, or the funding. All of those can be improved, and the improvements will not fix the underlying problem. Weather is a chaotic system which has a precise meaning. Tiny differences in the starting conditions grow exponentially over time. Edward Lorenz found this in 1961 when he restarted a simulation from printed values rounded to 3 decimal places instead of the 6 held in memory, and watched the run diverge completely from the original. The rounding error was smaller than any measurement he could have made of a real atmosphere. The growth rate has a name, the Lyapunov exponent, and from it you can calculate a horizon. For the atmosphere, it sits at roughly 2 weeks. Beyond that, the error in even a perfect model, fed by a dense global network of perfect instruments, swells until the forecast contains no information. You could measure every air molecule to the limit physics allows and still hit the same wall a little further out. Lorenz called it the butterfly effect, and the phrase has been misused so thoroughly that the original point tends to get lost. It is not that a butterfly causes a hurricane, it is that the difference a butterfly makes refuses to stay small. So this is not ignorance waiting to be cured. It is a structural feature of certain systems, and it applies to more than weather. Population dynamics, some cardiac rhythms, the long-term orbits of the planets. The solar system itself is chaotic, with a horizon of a few tens of millions of years. Determinism survives. Predictability does not. Halting problem. Every programmer has accidentally written a loop that never ends. It would be a genuinely useful tool that reads any program, looks at its input, and reports whether the thing will eventually finish or run forever. Compilers could warn you. Operating systems could refuse to launch it. Alan Turing proved in 1936 that no such tool can exist. The argument is a trap. Suppose the perfect halting checker exists. Build a new program that runs the checker on itself and then does the opposite of whatever the checker says. If the checker predicts it halts, it loops forever. If the checker predicts it loops, it stops immediately. The checker is wrong either way, so it cannot have existed. That short piece of reasoning marks off a region of permanently unanswerable questions, and the region is much larger than it first appears. Whether 2 programs do the same thing. Whether a piece of code ever accesses memory it should not. Whether a given configuration of a system will ever reach a particular state. All of these reduce to halting, and all are undecidable in general. The proof also handed computer science its central object. To reason about all possible programs, Turing first had to define what a program is, and the imaginary machine he built for that purpose still carries his name. This is why static analysis tools give you warnings rather than verdicts, and why formal verification requires humans to supply hints. The tools are not immature. They are working around a proof. Turing wrote it before a single electronic computer existed, which means the limits of computing were mapped out before computing itself was built. There is a practical cost as well. Antivirus software cannot decide in general whether code is malicious, so it matches patterns and guesses, and that is precisely why it fails. Rice's theorem. Suppose you decide the halting problem is too ambitious, and you settle for something modest instead. Not whether a program finishes, just whether it ever prints a particular word, or whether it always returns a positive number, something narrow, checkable, useful. Henry Rice proved in 1951 that you cannot have any of it. His theorem says that every non-trivial property of what a program computes is undecidable. Non-trivial simply means the property is true of some programs and false of others. If it is not true of absolutely everything or absolutely nothing, no general algorithm can determine it. Read that again slowly, because the scope is brutal. Not one specific hard question. Every question about behavior. Does this code compute the same function as that code? Does it ever produce an even number? Does it terminate on all inputs? Is it free of a certain class of bug? The moment the property depends on what the program does, rather than on how its text is arranged, the door closes. The proof works by reduction. Take any non-trivial property, and you can rig a program that exhibits it only if some other program halts. So an oracle for that property would quietly answer the halting question too. The industry has quietly organized itself around this. Type systems restrict what you are allowed to write so that certain questions become answerable. Test suites sample behavior instead of proving it. Analyzers report maybe. Every one of these is an admission that the general problem is closed and a strategy for getting useful work done inside a smaller pen. The bugs are not still there because nobody has been clever enough. They are there because clever enough was ruled out. Gödel's incompleteness. Mathematics was supposed to be the safe place. Whatever chaos there was in the physical world, arithmetic sat underneath it as bedrock. And the great project at the start of the 20th century was to prove that bedrock's solid. Write down the axioms. Show they never contradict each other. Show they settle every question. David Hilbert set it as the central task of the field. Kurt Gödel finished the project in 1931 by demolishing it. He showed how to encode statements about arithmetic as numbers within arithmetic, which let a formal system talk about itself. Then he constructed a sentence that, decoded, asserts its own unprovability. If the system proves it, the system is inconsistent. If the system is consistent, the sentence is true and unprovable. Either way, the dream is dead. Then he made it worse. The second theorem shows that no consistent system strong enough to describe arithmetic can prove its own consistency. You can only certify a system from outside, using a larger system, whose own consistency you then cannot certify either. It is turtles, permanently. Gerhard Gentzen later proved arithmetic consistent, using a stronger principle about infinite ordinals, which is a genuine result, and also exactly the move Gödel said would always be required. Turing's undecidability, which you just met, is a close relative dressed in machinery instead of logic. Both say the same thing from different directions. Formal reasoning has a horizon built into it. This has not stopped mathematics, and it has not made arithmetic unreliable in any practical sense. What it removed was a specific and very old comfort. There is no flaw under the floor, and there never was one to find. Hilbert's gravestone still reads that we must know, and we shall know. Bigger infinities exist. Counting feels like the simplest thing you ever learned, and infinity feels like the place where counting gives up. One infinity, endlessly large, the same in every direction. That was the general assumption, until a lonely mathematician in Halle decided to compare two infinite sets carefully. Georg Cantor asked whether the whole numbers could be paired one-to-one with the numbers on a line, decimals and all. He assumed such a list existed and then built a number guaranteed to be missing from it. Go down the list, take the first digit of the first number and change it, the second digit of the second number and change it, and so on forever. The result differs from every entry in at least one place. So the list was incomplete, and since the argument works for any list, no list can work. There are strictly more real numbers than whole numbers. Two infinities, provably different sizes. Cantor found an endless tower of larger and larger infinities above them, and the mathematical establishment of the time treated him as a menace. Leopold Kronecker blocked his career. Cantor spent stretches of his later life in a sanatorium. He also asked whether any infinity sits between the two. That question is called the continuum hypothesis, and the answer turned out to be that the standard axioms of mathematics cannot settle it in either direction. Gödel and Paul Cohen proved that much between them. His diagonal argument is now one of the most reused tools in mathematics. Gödel used the same maneuver. Turing used it. Every one of those proofs works by constructing an object that escapes any list claiming to contain everything. The technique that broke the safety of arithmetic started as a question about how many numbers there are. Route 2 Irrational. There is a story, almost certainly invented, about a man named Hippasus being thrown off a ship for what he discovered. Whether or not anyone drowned, the discovery was real, and for the Pythagoreans, it was a catastrophe. Their entire philosophy held that whole numbers and their ratios described everything. Draw a square with sides of length 1. The diagonal has a length that cannot be written as any fraction at all. The proof takes about 6 lines. Assume the diagonal equals some fraction reduced to lowest terms. Square both sides, and you find the numerator must be even. Substitute that back, and the denominator must also be even. But a fraction in lowest terms cannot have both parts even. The assumption destroys itself. It is the oldest proof by contradiction that anybody still teaches. What makes this devastating, rather than merely surprising, is that the diagonal obviously exists. You can draw it with a ruler in 2 seconds. It has a definite length. And that length is not expressible in the only language the Pythagoreans believed numbers spoke. Reality contained a quantity their system could not name. The Pythagoreans are said to have kept the discovery secret, which is the reaction of a religious order rather than a research group, and it tells you what was actually at stake. Most numbers turn out to be like this. Cantor's argument shows the fractions are a vanishingly thin dusting on the number line, while the irrationals make up essentially all of it. The numbers we handle comfortably are the strange ones, the rare, tidy cases. Everything else is an infinite, non-repeating decimal that no finite description will ever fully capture, sitting there, perfectly ordinary, one corner of a square away. Primes never end. Primes are the atoms of arithmetic. Every whole number is either prime or breaks down into primes in exactly one way, which makes them the closest thing mathematics has to a periodic table. They also thin out as you climb. Below 100 there are 25 of them, and by the time you reach the millions, the gaps are getting long. The natural worry is that they eventually stop. Euclid settled it around 300 years before the Common Era, and the proof is still the cleanest argument anyone has ever written. Suppose there is a complete finite list of primes. Multiply them all together and add 1. The new number leaves a remainder of 1 when divided by any prime on your list, so none of them divides it. Either it is prime itself, or it has a prime factor you missed. Either way, the list was not complete. Notice that the argument never hands you a prime. It only rules out completeness. That is the whole thing. 2,300 years old, requires no notation beyond multiplication, and has never been improved upon. It is taught in first-year courses in the same form Euclid gave it. One detail often gets garbled in the retelling. The proof does not claim the new number is itself prime, only that your list missed something, and counter-examples to the sloppier version turn up quite early. The primes remain the deepest unfinished business in mathematics. We know there are infinitely many, and we still cannot say precisely how they are spaced. The Riemann hypothesis, which is essentially a statement about that spacing, has stood unresolved since 1859. Something so simple that Euclid nailed it in a paragraph still hides a question nobody can answer. Quintic Unsolvable. You learned one formula in school and probably still remember fragments of it. Minus b plus or minus the square root of something, all over 2a. It solves any quadratic equation, mechanically, forever. Cubics have a formula too, uglier, found in a series of duels and betrayals in 16th century Italy. Quartics have one that barely fits on a page, then it stops. Paolo Ruffini argued it in 1799, and Niels Henrik Abel proved it properly in 1824. There is no formula for the general fifth-degree equation using only the ordinary operations and roots. Not a formula too long to write. Not one waiting to be discovered. None. Évariste Galois explained why, and his explanation created modern algebra. He looked at how the solutions of an equation can be shuffled among themselves without breaking any relationship between them, and found that this set of shufflings has a structure. For degree 4 and below, that structure comes apart into simple pieces in a way that mirrors peeling off one root at a time. At degree 5, it stops coming apart. The obstruction is not in the equation, it is in the symmetry. The collection of shufflings is called a group, and the property that fails at degree 5 is called solvability, which is where the word came from in the first place. Galois wrote much of this down the night before a duel and died the next morning at 20. His notes were dismissed twice, then published 14 years later, and eventually reorganized the entire subject. The lesson buried in it is that some things are impossible for reasons of shape, and you can only see the shape once you stop looking at the numbers. Squaring circle impossible. For more than 2,000 years, geometers tried to build a square with the same area as a given circle, using only an unmarked straight edge and a compass. The Greeks posed it. Arab and Indian mathematicians attacked it. Enough amateurs sent claimed solutions to the French Academy of Sciences that in 1775 the Academy announced it would no longer read them. The phrase squaring the circle became a byword for a hopeless task long before anyone could prove it was one. That proof arrived in 1882 when Ferdinand von Lindemann showed that pi is transcendental. A transcendental number is not the solution of any polynomial equation with whole number coefficients. Pi is not just irrational, it is outside the reach of algebra entirely. Straight edge and compass constructions can only produce lengths that come from repeated square roots, and every such length satisfies some polynomial. Since pi does not, the square root of pi does not either, and the required side length is not constructible. The task was not difficult. It was outside the set of things those two tools can generate, and had been since the day someone first drew a circle. Two other ancient puzzles fell the same way. Doubling the cube and trisecting an arbitrary angle were both shown impossible by Pierre Wantzel in 1837, using the same style of argument. Notice what happened there. A geometry problem was settled by a fact about the arithmetic nature of a number. in a field that did not exist when the problem was posed. 2 millennia of effort ended not with a construction, but with a proof that the effort had never had a target. People still send in solutions. The Academy was right to stop reading. Computation speed limit. Your laptop feels slow. It will feel slower next year, and the fix has always been the same, which is to wait for faster hardware. That reflex assumes the ceiling is far away and set by manufacturing. It is not. There is a ceiling set by physics, and it has been calculated. Norman Margolis and Lev Levitin proved in the 1990s that any physical system can change from one state to a completely distinguishable state no faster than a rate fixed by its energy. More energy buys more operations per second, and nothing else does. Not better engineering, not a cleverer architecture, not a different substrate. Energy is the currency, and the exchange rate is fixed. Seth Lloyd ran the numbers for what he called the ultimate laptop. 1 kilogram of matter, 1 liter of volume, all of its mass energy devoted to computation. The answer comes out at roughly a 1 followed by 51 operations per second, and the machine would be a fireball at 1 billion degrees. Your actual laptop is about 30 orders of magnitude below its own theoretical limit, which sounds like room to grow until you remember that everything between here and there involves turning your computer into plasma. There is a matching limit on memory. Lloyd worked out that the same kilogram could hold around a 1 followed by 31 bits, and that the two ceilings are linked because a machine cannot compute faster than it can shift information between its own parts. There is an odd comfort in it. Intelligence, artificial or otherwise, does not get to be arbitrarily fast. Thinking is a physical process. It costs energy, and the cost per thought has a flaw written into the same equations that describe everything else in this video. Bekenstein Bound. Take a hard drive and keep filling it. Then imagine improving the technology without bound, packing more and more into the same box. Atoms give way to something denser, then denser still. It feels like the only limit is manufacturing skill, and that the box could in principle hold anything. Jacob Bekenstein showed there is a maximum. The amount of information that can be contained in a region of space is capped by the energy inside and the size of the region, and if you try to exceed it, something dramatic happens. Keep adding information, which means adding energy, and eventually the contents collapse into a black hole. The box becomes an event horizon, and at that point, it is holding exactly the maximum, no more. The strange part is what the maximum depends on, not the volume, the surface area. A black hole's entropy, and therefore its information content, is proportional to the area of its horizon, measured in Planck units. Double the radius, and you get 8 times the volume, but only 4 times the storage. The capacity of a room scales with its walls, not its inside. Gerard at Hooft and Leonard Susskind push this into the holographic idea, proposing that a region of space might be completely described by physics living on its boundary. That part remains a conjecture. The area scaling that inspired it does not. Nobody expected that. Information ought to live in 3 dimensions, 1 bit per little cube. Instead, the universe books it by the square meter. Whatever is going on at the deepest level, the accounting is being done on a surface, and every physical thing in this video, including you, sits comfortably under a ceiling defined by an area you could in principle draw around yourself. Hawking radiation. Black holes were supposed to be forever. That was the whole idea. Gravity wins so completely that nothing escapes, so whatever falls in stays in, and the object sits there, cold and permanent, long after every star has gone dark. It was the one genuinely eternal object in the catalogue. Stephen Hawking took that away in 1974. Applying quantum field theory near the horizon, he found that the intense curvature separates pairs of virtual particles, letting one escape while the other falls in with negative energy. The result is a faint thermal glow leaking out, and the whole slowly losing mass to pay for it. Black holes evaporate. The temperature depends only on the mass, which is a remarkably tidy result for something so violent. The timescales are absurd. A hole the mass of the Sun has a temperature of about 60 billionths of a degree above absolute zero, which is far colder than the background radiation still filling space. So for now, it absorbs more than it emits. Only after the universe has expanded and cooled for an unimaginably long stretch does evaporation get going in earnest. The largest holes will take something like a 1, followed by 100 years to finish. Small holes behave in the opposite way. The lower the mass, the higher the temperature, so an evaporating hole runs hotter and faster as it shrinks and finishes in a burst. Nobody has ever seen one. But finish they do. That single result took the last permanent thing off the table. It also opened the deepest argument in modern physics, because the radiation appears to carry no information about what fell in, which would mean information is destroyed, which the rest of physics forbids. 40 years of work later, the argument is still running. Event horizon one way. You are falling toward a black hole, and there is a moment you cross the horizon. Nothing happens. For a large enough hole, the tidal forces at that point are gentle, the local physics is unremarkable, and there is no membrane, no flash, no marker of any kind. You would not be able to tell. What has changed is not your surroundings, but your options. Outside the horizon, you can point a rocket in any direction. Inside, every direction that exists for you leads inward. The center stops being a place you could travel to and becomes a time you are traveling toward. In the same way, tomorrow is. Escaping would require moving through your own past, which is not a matter of having a better engine. That switch is why the horizon is described as one way rather than as a barrier. Nothing pushes you in. Space and time have swapped roles in the mathematics, and the future simply lies in one direction. Light shone outward from just inside the horizon does not slow and fall back. It moves outward at the usual speed, through space that is carrying it in faster. The picture people reach for is a fish swimming upstream in a river that keeps accelerating toward a waterfall. Past a certain point, full effort upstream still means moving backwards. There is a strange consequence for anybody watching you from outside. They never see you cross. Your image slows, reddens, and fades, frozen at the edge for the remaining life of the whole. From your own point of view, you pass the point of no return without noticing, and the only sign was that everything you might have done afterwards had quietly become impossible. Causality speed limit. Light speed gets described as a speed limit for light, which makes it sound like a fact about photons. It is not. Light travels at that speed because light has no mass, and anything else without mass does exactly the same. Gravitational waves arrive at the same rate. So do gluons. The number is a property of space-time itself, which is why physicists increasingly call it the speed of causality. It is the maximum rate at which any influence, any signal, any consequence of anything can reach anywhere else. If the sun vanished this instant, the Earth would keep orbiting an absence for 8 minutes and change, because the news has to travel. Gravity is not exempt. The Earth would keep orbiting a field that was already gone, not an absence it had noticed. That single rule is what stitches the universe into a coherent story. Without it, effects could outrun their causes, and in some frames of reference arrive first. Every observer would file a different order of events, and nothing that happened would have a settled history. Relativity does not simply forbid faster travel. It forbids it because permitting it would let you kill your own grandfather with a sufficiently well-aimed message. There is a way of stating this that makes it feel less like a restriction. Everything moves through space-time at the same fixed rate, always. What varies is how that motion is divided between space and time. Sit still, and you are traveling through time at the maximum. Move quickly, and you trade some of that rate for movement through space. The limit is not a fence you run into. It is the total budget, and every object in the universe has already spent all of it. Moving clocks slow, 2 clocks, perfectly matched, sitting side by side on a bench. Take one on a journey and bring it back, and it will read differently. Not because it was shaken, or the battery drifted, or the mechanism suffered, because less time happened to it. Time dilation is the least negotiable consequence of the previous rule. If light must travel at the same speed for everyone regardless of how they are moving, then something else has to give, and what gives is duration. Imagine a clock made of a light pulse bouncing between 2 mirrors. Set it moving, and the pulse must travel a longer diagonal path to make each bounce, and since it cannot go faster, each tick takes longer. That is the whole derivation, and it is available to anyone with a ruler. The evidence is routine rather than exotic. Muons created high in the atmosphere live about 2 millionths of a second, which at their speed should let them fall a few hundred meters before decaying. They reach the ground in enormous numbers, because from our point of view, their internal clocks are running slow. In 1971, Joseph Heffel and Richard Keating flew cesium clocks around the world on commercial airliners and measured the difference against clocks left at home. It matched prediction. The flights cost less than $8,000, which makes it the cheapest confirmation of relativity anybody has managed. The unsettling part is that neither clock is wrong. There is no master clock somewhere keeping real time against which the others can be corrected. Duration is something each path through space-time accumulates for itself, and 2 people who separate and meet again will have genuinely lived different amounts. Time is not the stage. It is one of the things being measured. No universal now. You are on a train and someone is standing on the platform watching it pass. 2 small events happen, one at the front of your carriage and one at the back. From where you are sitting, they happen at the same instant. From the platform, they do not, and the gap is real. This is the relativity of simultaneity, and it is the piece of Einstein's argument that people find hardest, because it takes away something nobody knew they were holding. There is no universal present moment. The set of events you call now depends on how you are moving, and someone strolling past you at walking pace has a slightly different set. Speed up, and the difference grows. The everyday version is unmeasurably small. The cosmic version is not. For an observer moving slowly relative to Earth, the slice of now extending toward a galaxy billions of light years away can shift by centuries. 2 people walking past each other on a pavement have nows out there that differ by longer than recorded history. Neither is mistaken. Roger Penrose used this exact example to argue that the future must be as fixed as the past, since somebody's now is already out there containing it. What this dismantles is the picture of the universe as a single film reel advancing frame by frame for everybody at once. There is no shared frame. There is only space-time, with each observer carving it into their own private stack of moments at their own private angle. The idea of a present sweeping forward uniformly across everything that exists which sits under almost every human intuition about time, turns out to be a local convenience. It works because we all move slowly, and for no deeper reason than that. Gravity slows time. Your head is aging faster than your feet. Not by much. Over a lifetime spent standing upright, the difference amounts to a few billionths of a second, which no one will ever notice. It is nonetheless happening, continuously, and it has been measured in a laboratory over a height difference of about a foot. Gravitational time dilation comes from the equivalence principle, Einstein's realization that standing in a gravitational field is indistinguishable from accelerating. Clocks deeper in a gravitational well run slower than clocks higher up. Not apparently slower, slower. The effect was confirmed in 1959 by Robert Pound and Glenn Rebka, who measured the shift in gamma rays traveling up a lift shaft at Harvard. Satellite navigation would collapse without the correction. The clocks on those satellites run faster than ground clocks by about 45 millionths of a second per day from the weaker gravity, and slower by about 7 millionths from their orbital speed. The net is a gain of 38 millionths of a second daily, which sounds trivial until you multiply by the speed of light. Left uncorrected, positions would drift by roughly 10 kilometers every day. Every one of those satellites carries a clock deliberately tuned to the wrong rate before launch, so that it runs correctly once it is up there. The extreme version is what makes the film about the water planet more or less accurate. Sit close to a large enough mass, and time genuinely runs at a different rate for you than for everyone else. Come back, and the universe has moved on. There is no way to feel it happening from the inside, because your own clock, your own heartbeat, and your own thoughts are all slow together. It only shows up when you compare. Length contraction. Move fast enough, and the universe meets you halfway. This is the part of relativity that gets left out of the popular version, and it is the piece that makes everything else consistent. If time stretches for a fast traveler, distances must shrink for them, or the two of you would disagree about things that cannot be disagreed about. Length contraction is the name. An object in motion is measured to be shorter along its direction of travel by exactly the factor that time is dilated. The muons from the last few minutes make the point neatly. From our position on the ground, their clocks run slow so they survive the long fall. From the muon's own position, its clock is perfectly normal, ticking away its usual short life, but the atmosphere it is falling through is squashed to a fraction of its thickness. Two completely different explanations, same arrival. That is the test of whether a physical rule is real, rather than an artifact of viewpoint. Every observer must agree on what actually happened, even while disagreeing about durations and distances. Relativity works because the disagreements cancel with mathematical precision. Physicists call the quantities everybody agrees on invariants, and hunting for them is most of the job. There is a practical consequence for anyone dreaming of long journeys. Accelerate continuously toward another star, and the distance in front of you compresses. At sufficient speed, a trip that takes tens of thousands of years as measured from Earth can be crossed in a human lifetime, as measured on board. The galaxy is not actually out of reach. It is only out of reach in the sense that everyone you left behind will be gone when you arrive. Light speed, unreachable. Push something and it speeds up. Push twice as long and it goes faster still. Nothing in ordinary experience suggests this stops working, and for most of history, nobody had any reason to think it would. Keep pushing, keep gaining, eventually pass anything. The universe does not work that way, and the reason is the most famous equation ever written. Mass and energy are the same quantity in different clothes. When you put energy into a moving object, you are adding to its total energy, which means adding to its resistance to being accelerated further. The faster it goes, the more it fights back, and the curve is not gentle. It rises without bound as the speed of causality is approached. Massless things sidestep the problem by never having had a choice. They travel at the limit and cannot do anything else. Reaching that speed would require infinite energy for anything with mass, and infinite is not a large number, it is an unavailable one. Particle accelerators demonstrate this every day. The machine at CERN pushes protons to within a hair of the limit, close enough that they complete 11,000 laps of a 27-kilometer ring every second, and the last increments of speed cost preposterous amounts of power for almost no gain. The energy goes into mass instead of motion, which is precisely why colliders are useful. That surplus energy, delivered in a collision, converts into new particles that were not there before. The limit that stops you going faster is the same rule that lets you manufacture matter out of movement. Every discovery those machines have made, including the Higgs boson, exists because the speed of causality refused to let the protons go any quicker, and the energy had to end up somewhere. Galaxies already lost. Somewhere out there tonight is a galaxy that you could chase forever at the speed of causality and never reach. Not because it is far away, though it is. Because the space between you and it is being created faster than any signal can cross it, and the deficit grows every year. Expansion is not galaxies flying apart through space. It is space itself stretching everywhere at once, and the rate accumulates with distance. Two objects far enough apart recede from each other faster than light, without either one breaking any rule, because neither is moving through space quickly. Nothing local is violated. The separation simply grows. That produces a boundary called the cosmological event horizon. Anything beyond it has already left the part of the universe you can ever interact with. Light leaving it now will never arrive, no matter how long you wait. Current estimates put the number of galaxies already past that line in the region of 94% of everything we can presently see. We are watching old light from things that are, in every meaningful sense, gone. It gets lonelier from here. Dark energy is accelerating the expansion, so the horizon draws inward over cosmic time. Eventually, every galaxy outside our own local group will cross it and fade from view. Astronomers on some far future world will look up at a sky containing one merged galaxy and empty blackness beyond, with no evidence anywhere that the universe was ever expanding or that anything else existed. They will do good science and reach entirely wrong conclusions, and they will have no way to know. We happen to be living in the window when the evidence is still visible. Universal heat death. Everything ends, but not in the way films suggest. There is no bang at the finish, no collapse back to a point, no dramatic close. Current measurements point to expansion continuing indefinitely, and the ending is not an event. It is a slow settling into a condition from which nothing further can happen. The sequence has been mapped out in some detail. Star formation slows and stops once the gas runs out, in perhaps 100 trillion years. The last red dwarfs burn down. What remains is a scatter of dead stars, black holes, and drifting debris, occasionally colliding, gradually flung apart by gravitational interactions. Black holes evaporate over the timescales you heard about earlier. Matter itself may decay, though nobody has yet seen a proton do it. What is left afterwards is a thin, cold, expanding fog approaching a uniform temperature just above absolute zero. This is heat death, and the name is misleading because there is no heat left in any usable form. Energy still exists. It is simply spread out so evenly that no part of the universe is hotter than any other part, and without a difference, there is nothing to drive a process. Freeman Dyson once asked whether a sufficiently patient intelligence could keep thinking forever by slowing itself to match the cooling, and the accelerating expansion appears to have closed that door as well. That is the real definition of the end. Not the absence of energy, but the absence of gradients. Every engine, every star, every living cell, every thought you have ever had, has run on a difference between here and there. When the differences are gone, the possibility of anything happening is gone with them, and the universe continues to exist for an eternity in which nothing whatsoever occurs. Entropy only increases. Stir milk into coffee and watch the swirl smooth out into an even brown. Keep stirring. It never separates back. You have never once seen it happen, and neither has anyone else in the history of the species, and there is nothing in the underlying physics that forbids it. That is the puzzle at the heart of the second law of thermodynamics. Individual particle collisions are perfectly reversible. Run the equations backwards and they work fine. Yet the collective behavior has a direction so reliable that it is the single rule physicists would defend hardest. Arthur Eddington wrote that if your theory contradicts the second law, there is nothing for it but to collapse in deepest humiliation. The resolution is about counting, not about forces. There are astronomically more ways for milk to be mixed than for it to be gathered in a neat blob. Entropy measures the number of microscopic arrangements consistent with what you see from outside. Systems drift toward mixed states not because something pushes them there, but because mixed states are overwhelmingly more numerous. Unmixing is not impossible. It is so unlikely that waiting for it would take vastly longer than the universe has existed. Ludwig Boltzmann worked this out and was attacked for it throughout his career. He killed himself in 1906, and the equation is carved on his headstone. This is why the second law feels different from the others in this video. It is not a fundamental prohibition. It is a statement about odds so lopsided that they function as a law, and it is why perpetual motion, refrigeration without power, and every free energy scheme fail. They are all attempts to talk a system into a rare configuration, and the numbers involved are simply not survivable. Arrow of time. Physics has an odd blind spot. Almost every fundamental equation works identically whether time runs forwards or backwards. Newton's laws, Maxwell's equations, general relativity, the Schrödinger equation. Film a collision between two billiard balls, play it in reverse, and nothing in the footage breaks a rule. Yet the world is emphatically not like that. Eggs break and do not unbreak. You remember yesterday and not tomorrow. Heat moves from hot to cold and never the other way. Something is producing a direction, and the equations are not the source. The best answer available is that the direction comes from the second law, and the second law's direction comes from an initial condition. The universe began in an extraordinarily low entropy state, extremely smooth, extremely uniform, with almost none of the structure it has now. From that starting point, there is essentially nowhere to go but toward more disorder, and everything we call the flow of time is the working out of that slide. The past is the direction in which entropy is lower. That is the definition, and it is the only one anybody has that holds up. Your memories are a physical record, and recording requires an entropy increase, which is why memory points the way it does and not the other way, which puts the question one level further back, unanswered. Why did the universe start in such a special state to begin with? Nobody knows. Roger Penrose has calculated how improbable that starting configuration was and produced a number too large to write conventionally. So the reason you cannot revisit last Tuesday traces back, through thermodynamics, to a condition at the beginning of everything that remains unexplained. Time has a direction because of an accident nobody can account for. Forgetting costs energy. Deleting a file feels free. It happens instantly, nothing is consumed, and the only physical trace is that a light on a drive blinks. It is the emptiest possible action, removing something rather than making it, and it seems obvious that erasing cannot cost anything. Rolf Landauer proved in 1961 that it does. Erasing one bit of information necessarily releases a minimum quantity of heat, proportional to the temperature. The reason is elegant. Computation that merely rearranges information is reversible in principle and can be done at arbitrarily low energy cost. But erasure takes two possible states and maps them to one. Information is lost, the process cannot be undone, and thermodynamics charges for that irreversibility. The number is small, around 0.003 of an attojoule per bit at room temperature, roughly 1 billion times below what real chips currently spend. It has nevertheless been measured. In 2012, a team using a single microscopic particle in an optical trap confirmed the limit experimentally, and later work has tightened the result. The gap between that flaw and real hardware is where nearly all the waste in modern computing lives, and it is why data centers need cooling at all. What makes this a genuinely great discovery is what it unified. Before Landauer, information was an abstraction, and thermodynamics was about steam engines. Afterwards, they were the same subject. Information is physical. It lives in arrangements of matter. It obeys conservation rules, and destroying it has a thermal price with a published rate. Every notification you dismiss, every cache your phone clears, every memory a brain lets go of, pays a tiny toll in waste heat that the universe collects without exception. Nothing gets forgotten for free. Maxwell's demon loses. A demon sits at a tiny door between two rooms of gas at equal temperature. It watches the molecules, and whenever a fast one approaches from the left, it opens the door and lets it through. Slow ones from the right get the same treatment in reverse. No work is done on the gas. The door is frictionless and massless. After a while, one room is hot and the other is cold. From nothing. James Clerk Maxwell invented this creature in 1867, and for a long stretch, it looked like a genuine hole in the second law. You now have a temperature difference, which means you can run an engine, which means free energy forever. Finding the flaw took the better part of a century and produced several wrong answers along the way. Leo Szilard showed in 1929 that measuring which molecules are fast must itself cost something. Later, work suggested the measurement could in principle be done cheaply. The final answer, from Charles Bennett in 1982, is the one that holds. The demon has to record what it observes, and its memory is finite. Sooner or later, it must erase, and by Landauer's principle, erasure dumps exactly enough heat to balance the books. Bennett's insight was that the measurement itself can be made reversible, which pushes the entire cost into the erasure and nowhere else. The demon is not defeated by friction, or by clumsiness, or by any practical difficulty. It is defeated by having to forget. A century and a half of effort to cheat thermodynamics ended with the discovery that thought itself is thermodynamic, and that the ledger includes the mind of whoever is trying to cheat. Carnot Limit. Engineers have been chasing efficiency since the first steam engine coughed into life, and the assumption behind that chase has always been that better materials and tighter tolerances will keep buying improvement, reduce the friction, improve the seals, shrink the losses. It sounds like a project without an end. Sadi Carnot ended it in 1824 in a book that sold almost no copies and was then largely forgotten for 2 decades. He worked out that the maximum possible efficiency of any heat engine depends only on the temperatures it runs between. Not the fuel, not the design, not the working fluid. Only the ratio of the cold temperature to the hot one. The number that falls out is sobering. A modern combined cycle power station runs at around 1,500 degrees Celsius and rejects heat near ambient, giving a theoretical ceiling around 80%. Real plants reach roughly 60%, which is remarkably close. A car engine runs cooler and its ceiling is far lower, which is why most of the petrol you buy leaves as heat rather than motion. That is not a design failure. It is the tax. Heat pumps look like they beat it and do not, because they move heat around rather than converting it into work. What makes Carnot's result extraordinary is its timing. He wrote it before anyone understood what heat actually was, while the caloric theory still held sway, treating heat as an invisible fluid. He got the right answer from an entirely wrong picture, because he reasoned about what would happen if the limit could be beaten, and found it would let you build a machine that produces useful work from nothing. He was 28, and he died of cholera 8 years later. Perpetual motion impossible. The British Patent Office has a standing rule that it will not consider an application for a perpetual motion machine unless a working model is supplied. The French Academy stopped reviewing them in 1775, alongside the circle squaring submissions. Both institutions arrived at the policy the same way, by exhaustion. There are 2 kinds of impossible machine, and they fail for different reasons. A machine of the first kind produces more energy than it consumes, which violates conservation. A machine of the second kind takes heat from a single reservoir and converts all of it into work, which conserves energy perfectly and violates the second law instead. The second kind is the seductive one, because on paper, the arithmetic balances. It is also the one that would let you power a ship by cooling the ocean. Shipping would be free forever, and the sea would gradually freeze behind every vessel that used it. The designs recur with remarkable consistency across centuries. Overbalanced wheels with weights on hinged arms, first drawn in 12th century India and still being filed today. Self-flowing waterfalls, magnetic motors. Every one of them contains a place where the builder stopped accounting carefully, and finding that place is a decent hobby. The interesting thing is not that they fail, but why the failures are so uniform. Conservation of energy is not an empirical generalization that has happened to hold up. As you are about to hear, it follows from something deeper about the structure of physical law, which means a working perpetual motion machine would not merely embarrass a few textbooks. It would mean the universe treats one moment in time differently from another, and nothing else we know is consistent with that. Energy conserved. Energy is the strangest item on this whole list, because everyone uses the word constantly and almost nobody can say what it is. It is not a substance. You cannot isolate a jar of it. Richard Feynman was blunt about this, pointing out that physics has no idea what energy actually is, only that there is a number you can calculate which never changes. That number is the first law of thermodynamics. Energy is neither created nor destroyed, only moved and converted. Chemical to thermal in a fire, gravitational to kinetic in a fall, kinetic to electrical in a turbine. Track it carefully through any process, and the total at the end matches the total at the start, provided you remember to count the waste heat that nobody wants. Even the exceptions turn out not to be exceptions. Nuclear reactions appear to create energy from nowhere until you notice the products weigh slightly less than the reactants, and mass was energy all along. Chemical bonds work the same way at a scale too small to weigh. Burn a log, and the ash and smoke together weigh very slightly less than the wood and the oxygen did, by an amount no scale on Earth can detect. The one genuine complication is cosmological. On the largest scales, in an expanding universe, energy conservation becomes awkward to define, because the theorem that guarantees it depends on a symmetry the expanding universe does not quite have. Light stretched by expansion loses energy, and there is no agreed answer about where it goes. That is not a loophole anyone can exploit from inside a laboratory. It is a hint that this most reliable of rules rests on something even more basic, which somebody worked out over a century ago. Symmetry conserves quantities. In 1918, in Göttingen, a mathematician who was not permitted to hold a paid professorship because she was a woman proved the result that explains why conservation laws exist at all. Emmy Noether had been brought in by Hilbert and Klein specifically to sort out a problem in general relativity, and she solved considerably more than that. Her theorem says that every continuous symmetry of a physical system corresponds to a conserved quantity. That sentence looks technical and is actually a hinge. If the laws of physics work the same today as tomorrow, meaning they are symmetric under shifts in time, then energy is conserved. If they work the same here as over there, momentum is conserved. If they work the same whichever way you face, angular momentum is conserved. So conservation is not a separate set of facts bolted onto the universe. It is a consequence of the universe not caring where or when or in which direction you set up your experiment. Turn that around and it becomes a diagnostic. Whenever physicists find a quantity that is conserved, they go looking for the symmetry behind it, and that search has driven most of particle physics since. The Higgs boson was found that way, starting from a symmetry that needed to be broken and a mechanism capable of breaking it. Noether was eventually driven out of Germany in 1933 and taught in Pennsylvania until her death 2 years later. Einstein wrote to the New York Times calling her the most significant creative mathematical genius so far produced since the higher education of women began. Her theorem is now taught in every graduate physics course, and most undergraduates have never heard her name. Forces come paired. You push against a wall and the wall pushes back, with exactly the same force, in exactly the opposite direction. This is the third of Newton's laws, and it is the one that sounds most like a slogan and is most often misunderstood. People hear it as a moral principle about consequences. It is a statement about pairs. Forces do not happen to objects. They happen between objects, always in twos, always equal, always opposite. The Earth pulls you down, and you pull the Earth up with identical force. The reason you fall and the planet does not visibly move is mass, not the size of the pull. A rocket does not push against the air behind it, which is why rockets work in vacuum. It throws mass out of the back, and the mass throws the rocket forward. The law is really momentum conservation wearing different clothing, and by Noether's theorem that traces to the fact that the laws of physics are the same in every location. Move your experiment across the room and nothing changes, therefore momentum is conserved, therefore forces come in balanced pairs. 3 centuries of separate rules turn out to be one idea seen from different angles. Newton did not know any of that. He stated the third law as a bare observation, and it took 2 centuries and a mathematician he never met to explain why it is true. There is a version of this that survives into modern physics with a twist. In electromagnetism, the forces between 2 moving charges can appear unbalanced, which looks like a violation until you account for the momentum carried by the field itself. Add that in, and the ledger closes exactly. the pairs still hold. One of the partners is simply not made of matter. Angular momentum conserved. A skater pulls her arms in and speeds up. Nobody pushes her. She does not use the ice. The acceleration comes from nowhere visible, and it happens every time, reliably enough that the entire sport depends on it. Angular momentum is conserved, and it depends on both how fast something rotates and how its mass is distributed. Pull mass closer to the axis, and the rotation must quicken to keep the product fixed. Extend it again, and she slows. By Noether's theorem, this traces back to the fact that space has no preferred direction. Rotate your laboratory, and physics is unchanged. Therefore, this quantity persists. The consequences run to enormous scales. A cloud of gas collapsing under gravity spins faster as it shrinks, which is why almost everything in the universe rotates, and why solar systems form as flat disks rather than spheres. A dying star's core collapsing to a few kilometers across ends up rotating hundreds of times a second, which is what a pulsar is. The Earth turns today because the cloud that formed it was turning, and there is nothing available to stop it. The moon is slowly stealing some of that rotation through the tides, which is why our days are lengthening by about 0.002 of a second per century. At the smaller scale, the rule becomes stranger still. Particles carry an intrinsic angular momentum called spin that has nothing to do with anything actually rotating, and it comes only in fixed steps of a fundamental unit. It cannot be reduced, shared out, or switched off. An electron has been carrying the same amount since it came into existence, and the only way to change the total in the universe is to change what particles exist. Charge conserved. Charge is the most stubborn quantity anyone has measured. Energy can appear and disappear locally within the bounds of the uncertainty principle. Particles can be created and destroyed wholesale. Through all of it, the total electric charge in an isolated system has never been observed to change by the smallest fraction. The precision here is extraordinary. Experiments looking for an electron decaying into lighter neutral particles have found nothing, and the limits now put the electron's lifetime at something like a 1 followed by 28 years, which is far longer than the universe has existed. Charge conservation is also exact in a way that some other rules are not. It is not approximate, not statistical, not a very good approximation at low energies. It holds. No experiment in any laboratory has ever recorded so much as a single deviation. By Noether's theorem, the symmetry underneath it is a peculiar one. It is not about space or time, but about a hidden freedom in the electromagnetic field, a choice of internal phase that can be adjusted anywhere without changing anything measurable. That kind of symmetry is called a gauge symmetry, and it turns out to be the pattern behind all the forces in the standard model. Charge is conserved because that internal freedom exists, and the photon exists for the same reason. Antimatter obeys the rule rather than breaking it. A particle and its antiparticle carry opposite charges, so creating a pair from energy adds nothing to the total, and annihilating one removes nothing. Every violent process in every star and every collider has kept the books balanced. Whatever is going on at the foundations, this particular number was set at the beginning and has not moved since. CPT Theorem. Take the universe and hold it up to a mirror. Swap every particle for its antiparticle. Run time backwards. Do all three of those at once, and the result must obey exactly the same laws as the original. This is the CPT Theorem, and it is about as close to sacred as physics gets. The remarkable part is what happens when you do them one at a time. For a long stretch, it was assumed each was a symmetry on its own. Then, in 1956, Chien-Shiung Wu ran an experiment on cooled cobalt nuclei and found that the weak force distinguishes left from right. Mirror symmetry is broken, plainly and dramatically. A few years later, the combination of mirror and antimatter symmetry was found broken too, in the decay of neutral kaons. Only the full triple has survived. CPT is not merely an observation, but a consequence of relativity and quantum field theory together, which means breaking it would tear down the framework rather than merely amend it. Every test has confirmed it, including comparisons of the mass of a proton and an antiproton agreeing to about 1 part in a billion. Antihydrogen has now been made and studied at CERN, and it behaves exactly as the theorem demands, down to falling in the same direction as ordinary matter. There is one dangling thread that keeps physicists awake. The broken combination of mirror and antimatter symmetry allows matter and antimatter to behave slightly differently, which is presumably why anything exists at all, rather than everything having annihilated in the first second. The trouble is that the amount of asymmetry we have measured is nowhere near enough to account for the amount of matter we can see. Something else happened, and nobody knows what. Every electron identical. Every electron ever measured has been identical to every other electron, to the limits of measurement. Same mass, same charge, same spin, no serial number, no where, no history. This is not a claim about manufacturing tolerance. It is a much sharper statement, and it is genuinely difficult to get your head around. Two identical particles are not merely similar, they are indistinguishable in a technical sense with consequences you can measure. Swap 2 electrons in a system, and there is no experiment, in principle or in practice, that can detect the swap. Because of that, the mathematics cannot treat them as separate labeled objects, and the way the equations handle the exchange is what produces the exclusion rule from earlier and the entirely different behavior of particles like photons, which pile into the same state happily. All of chemistry sits on top of that split. John Wheeler once phoned Feynman with an explanation. Perhaps there is only one electron in the universe, threading backwards and forwards through time, appearing as every electron at once. It does not survive scrutiny, since it predicts equal numbers of electrons and positrons, but it captures the flavor of the problem correctly. Feynman used the idea anyway, treating a positron as an electron moving backwards through time, and it turned out to be extremely useful bookkeeping. The deeper answer from quantum field theory is that particles are not objects at all. They are excitations in a field that fills all of space, the way ripples are excitations in water. 2 ripples in the same pond are identical because they are the same pond doing the same thing twice. Nothing needs to be manufactured to a tolerance because nothing was ever manufactured. Life chose handedness. Hold up your hands with the palms facing you. They are mirror images, and no amount of rotating will make one sit exactly on top of the other. Chemistry has the same property. Many molecules come in left-handed and right-handed versions with identical formulas, identical bonds, and identical energies. Life uses one hand. Nearly every amino acid in every organism on this planet is the left-handed form. Sugars in DNA and RNA are right-handed. This is not a slight preference or a statistical lean. It is essentially universal, from bacteria in deep rock to the cells reading this sentence, and it has been that way for as long as there has been life. The reason it matters is that biology is built on shape. An enzyme grips its target the way a hand grips a glove, so the wrong-handed version does not fit and often does something else entirely. The thalidomide disaster is the case everybody cites, where one form treated morning sickness and the mirror form caused severe birth defects. Carvone is the harmless illustration. One hand smells of spearmint, the other of caraway, from the same atoms arranged in mirrored order. Your nose contains receptors that are themselves handed, which is the only reason the difference is detectable at all. Nobody knows why life chose. Ordinary chemistry produces both forms in equal amounts, so something broke the tie. Proposed culprits include polarized starlight in the cloud that formed the solar system, the weak force's own left-handed bias filtering down from particle physics, or simple chance amplified by the fact that a self-replicating system using one hand outcompetes a mixture. The tie was broken once, very early, and never revisited. Kleiber's law. A mouse burns through its life at a furious rate. Its heart runs at 600 beats a minute. It eats a substantial fraction of its body weight daily, and it is dead within a couple of years. An elephant does everything slowly and lives for decades. The obvious guess is that metabolism scales with body mass, twice the animal, twice the energy. It does not. Max Kleiber measured this carefully in the 1930s and found that metabolic rate scales with mass raised to the power of 3/4. Double an animal's mass and its energy use rises by only about 80%. The relationship holds across an astonishing range from microbes to blue whales, spanning more than 20 factors of 10 in size, and it holds for plants as well. Larger animals are therefore more efficient per kilogram, and they pay for it with slower everything. Heart rate, breathing rate, and lifespan all scale with mass to roughly the -1/4. Multiply those together and something odd emerges. Most mammals get through approximately the same number of heartbeats in a lifetime, somewhere around 1 billion, whether they spend them quickly or slowly. Humans are the notable exception, running roughly 3 times over that budget. Why the exponent is 3/4 rather than the 2/3 you would expect from surface area is still argued over. The leading explanation involves the geometry of branching supply networks, blood vessels and airways and plant vasculature, all of which fill a 3-dimensional body from a single source and hit the same mathematical constraints. Whatever the cause, the rule is unusually rigid for biology, which is a field that normally resists this sort of tidiness. Square cube law. Giant insects are a staple of bad films, and the reason they stay in films is arithmetic that was worked out 4 centuries ago. Galileo wrote it down in his final book, published while he was under house arrest, and it is the reason nothing can simply be made bigger. Double the length of an object, and its surface area goes up 4 times, while its volume, and therefore its weight, goes up 8 times. Every property that depends on area falls behind every property that depends on volume. This is the square cube law, and almost every limit on size traces back to it. The consequences are everywhere once you know to look. Bone strength depends on cross-sectional area, so a scaled-up animal's legs would snap under their own weight, which is why elephants have thick pillar-like limbs, and gazelles have spindly ones. Insects breathe through passive tubes that carry oxygen only a short distance, so an ant the size of a dog would suffocate. Small animals lose heat quickly because they have enormous surface area relative to volume, which is why shrews must eat almost constantly, and why there are no tiny mammals in the Arctic. It cuts the other way too. A mouse can fall down a mine shaft and walk away because air resistance depends on area and the impact energy depends on mass. J.B.S. Haldane made exactly that point in an essay called On Being the Right Size, and his conclusion is the general one. For every animal and for every machine, there is a size at which it works, and the design is downstream of the size rather than the other way around. Cells count down. Size is one limit on a body. Time is another, and it turns out to be written into the cells themselves. For the first half of the 20th century, the accepted view, backed by a famous and badly run experiment, was that cells kept outside a body would divide indefinitely. Immortality was thought to be the natural state of a cell, and aging something that happened only to whole organisms. Leonard Hayflick overturned that in 1961. Normal human cells in culture divide roughly 40 to 60 times and then stop permanently. They do not die. They enter a state called senescence, still alive, still metabolizing, no longer dividing. The finding was rejected by the leading journal of the day before being published elsewhere, and it took years to be accepted. The mechanism turned up later. Chromosomes end in repeated sequences called telomeres, which act as a buffer, and the copying machinery cannot quite reach the very end of a strand. Every division shaves a little off. When the buffer runs out, the cell stops, rather than risk damaging real genetic information. It is a counter, and it is counting down. That counter is a defense. Cells that break it and divide without limit are, by definition, what cancer is. And most cancers do exactly that by switching on an enzyme called telomerase that rebuilds the ends. So the limit on how long a tissue can renew itself and the protection against runaway growth are the same mechanism viewed from two sides. Any treatment that lifts the ceiling on division lifts the brake on tumors at the same time, which is why the obvious idea has never been simple. Absolute zero unreachable. Physicists have been racing toward the bottom of the temperature scale for over a century, and the records now sound absurd. Laboratories routinely reach a few billionths of a degree above absolute zero. One experiment in 2021 cooled a cloud of atoms to about 38 trillionths of a degree. Each new result gets closer, and none of them arrive. The third law of thermodynamics says they never will. Absolute zero is not merely difficult to reach, it is unreachable in a finite number of steps. Every cooling technique works by removing entropy from a system and dumping it somewhere else, and as the temperature falls, each additional step removes less. The effort required grows without bound as the target approaches. You can halve the distance forever and never close it. Quantum mechanics gives the same answer from a different direction. A system at exactly absolute zero would be completely motionless, and the uncertainty principle from earlier does not permit that. Even the lowest possible state retains its zero-point motion. So the floor is not merely hard to touch, there is nothing there to touch. The bottom of the scale is defined rather than visited, fixed by the definition of the Kelvin rather than by any thermometer that has been there. What makes the pursuit worthwhile is that the last few billionths are where the interesting things happen. Superconductivity, superfluids, and Bose-Einstein condensates all appear down there, where quantum behavior stops being confined to individual particles and takes over whole clouds of matter at once. The coldest known places in the universe are all inside laboratories on this planet, colder by far than deep space, and every one of them is asymptotically approaching a destination that does not exist. Goodhart's law. A hospital decides to measure how long patients wait in the emergency department and sets a 4-hour target. Waiting times promptly improve. Then somebody looks closely and finds patients being admitted to wards they do not need, or held in ambulances outside the door where the clock has not started, or discharged in a hurry at 3 hours and 50 minutes. Charles Goodhart, an economist at the Bank of England, put the general form of this in 1975. When a measure becomes a target, it ceases to be a good measure. Marilyn Strathern gave it that crisp phrasing later, and the pattern has been rediscovered independently in education, policing, software, and every organization that has ever tried to manage something it cannot directly see. The mechanism is not dishonesty, though dishonesty helps. Any measure is a proxy, a visible thing that correlates with an invisible thing you actually care about. Waiting time correlates with quality of care. Test scores correlate with learning. Lines of code correlate with work done. The moment you attach consequences to the proxy, effort flows toward the proxy, and the correlation you were relying on quietly comes apart underneath you. Soviet nail factories judged on total weight are said to have produced enormous nails, and factories judged on count produced tiny ones. The anecdote is probably embellished. The pattern is not. This one is not a law of physics, and it can be softened with multiple measures, judgment, and short feedback loops. But it cannot be escaped, because the escape would require a proxy that is identical to the thing itself, at which point it is not a proxy. Anything you can count is a shadow of something you cannot, and the shadow moves the moment you start rewarding it.